lesson 4, we looked at what exponential functions look like. Now we're going to look at what logarithmic functions look like, and just comparing what the base might do to each of the functions, as well as what a coefficient out front might do. And then we're just going to study odd and even cases of logarithms. So, you guys ready for this? Xander? Okay, cool. Alright, so we're first going to be looking at the logarithm with base 3, argument x. If we take a look at that graph, y equals log base 3x, it passes through the point 3, 1, and the reason why is because if we take a look at x and y, and we were to convert this into exponential form, if we put 3 to the power of 1, would that equal 3? Yeah. Okay, so this is our y, this is our x. So continuing on with that, we're just going to explore how the graph changes when we change our base. So the original graph, can you guys tell me what your x-intercept is? Where are we crossing the x-axis? 1, 0, perfect. Okay, and then we noted that we had a point going through positive 3, 1, 2, 3, and 1. Okay, let's see what happens when we change the base to base 10. They're telling us that y is equal to 1, so let's replace that into the logarithm. We got 1 equals log base 10x. And if we convert that to exponential function or form, we can get 10 to the power of 1 equals x. So when y equals 1, x equals 10. So on the graph of y equals log base 10 argument x, we know there's a point at 10, 1. Let's mark that up. Let's just figure out if it has the same x-intercept. What do we know about x-intercepts? What does y always equal? 0. Okay, so we're going to use this equation and set y equal to 0. And then we're going to solve for x. Okay, put that into exponential form. 10 to the power of 0 is equal to x. Anything to the power of 0 is 1. So our x-intercept, again, is that, 1. Okay, 1, 0. What do we know also about logarithms? Where do they approach? What do we call? Good, it's a vertical asymptote. And this equation is the line x equals 0. Okay, so we have a vertical asymptote at x equals 0. So if I'm going to connect my y-intercept to the point that we just solved for, 10, 1, I know it's going to approach the vertical asymptote, it's going to go through that x-intercept, and it's going to line up with the point that we solved for, 10, 1. And then we should label that. That is the graph of y equals log base 10, argument x. It's getting closer to the x-axis. Okay, let's figure out the point when y is 1 for the graph with base 1/3. So again, we're going to replace y with 1. Then we're going to convert it to exponential form and solve for x. So we have 1/3 to the power of 1 equals x. So what's x? 1/3. So let's mark out that point. We have 1/3 and a 1. Okay, so that's about here, up at 1. If I were to calculate my x-intercept, again, y equals 0. And now with the base of 1/3, we just convert that to exponential form. 1/3 to the power of 0 is equal to 1. So, one more time, our x-intercept is going through 1, 0. So the unique property about this graph is that it actually going through this way. So just looking at the logarithm base 3 compared to the logarithm with base 1/3, can you guys predict what's happened? Maybe what kind of transformation it is? Any guesses? Okay, this is our original graph. Perfect, a reflection over the x-axis. And what we're going to learn is anytime you have a reciprocal in the bases, it's just a reflection over the x-axis. So if you had to predict where the graph of y equals log base 10x was compared to log base 1/10x, we would predict that it's a reflection over the x-axis. But let's just prove that. Hey, have you guys noticed a pattern? What your x value is? So here my base was 1/3, my x value is 1/3. Here my base was 10, my x value was 10. Here my base was 3, my x coordinate was 3. So what's your x coordinate here? 110. So we're going to mark out that point, 110 and 1. So that's about here. Are we going to have an x-intercept at 1, 0? Yeah?
Yeah.
Okay, and again, that's because 0 equals our logarithm, 1/10 of x. And then we take our base, raise it to the power of 0, and anything to the power of 0 is just 1. So we get the same x-intercept. Okay, and then it's going to approach that vertical asymptote, go through the 2 points that we marked out. I didn't quite get the accurate reflection, but it's pretty close. This is the graph of y equals log base 1/10, 1/10, argument x. So I'm just going to scroll down in the lesson. Actually no, I don't want to do that. I'm just going to point out what we're going to talk about here. So the table of values here, it's asking for, depending on which function, what's the domain, the range, the x and y intercepts, the asymptote, and the x value when y equals 1. Okay, if you were to look at every single logarithmic graph here, what is the domain?
Just greater than 0.
Yep, x is greater than 0. And that's because we have a vertical asymptote at x equals 0. So for our asymptote, we can put x equals 0. What's your range? All real numbers. For every single graph, the range is an element of all real numbers. Do we have an x-intercept?
Yep.
What was the x-intercept for every single graph? 1, 0. Do we have any y-intercepts? And the reason why is because we have a vertical asymptote at x equals 0. So if we can't touch the y-axis, we can't have a y-intercept. So there's none. And for all of them, what did we notice that the x value of the coordinate was when y equals 1? For example, when y equals 1 here, what was the x value related to? The base of the logarithm. Same thing here. When y is 1, the base is your x value. When y is 1, the base is your x value. So we would say, at the very bottom of this table, that the x value is always b. So as an ordered pair, you could write it as b1 if you wanted. So for part D and E, going on the next page, what kind of transformation did we talk about if we were to compare the graph of log base 3 compared to the graph of log base 1/3? What's the transformation? Hannah? So if we have base 3 and base 1/3, how did they look?
Your reflection of the x-axis or y-axis or no x-axis.
X-axis. You sure?
Yeah.
Yeah, x-axis. Okay, one was going like this, and the other one was like this. So that's telling us it's a reflection over the x-axis. What was your invariant point? The x-intercept. That was the point that stayed the same on both. Okay, if we were to compare logarithm with a base 10 compared to a logarithm with base 110, again, it's a reflection over the x-axis. So for both of these, you can just write it's a reflection over the x-axis. Part F is just pretty much saying fill in the blank that it was a reflection over the x-axis. And part G, let's talk about our point mapping. If we are reflecting over the x-axis, what value is going to change? The y. So we're going to go from xy to x negative y. So all the y coordinates will change. Do you guys remember if we had y equals f of x, and we were trying to show a reflection in the x-axis where that negative would go? In front, good. So we'd have y equals negative f of x. So that's no different here than right here with our identity. We're saying that the logarithm of 1 over b as our base, argument x, is equal to a negative logarithm base b of x. So the important thing is that these are reciprocals. And you could have written this the other way too. You could have had the logarithm of 1 over b argument x is equal to the logarithm base b argument x. But instead of the negative being here, we're going to put that out front here. Both are equivalent. You can divide the negative from left side to right. So we're going to start this next question without solving by using exponents. They're telling us that the logarithm base 4 of x is equal to 8. And we have to state the value of the logarithm where the base is now 1 over 4 of x. So let's just start with this here. Okay, the logarithm of 1 over 4x is equal to the negative logarithm base 4 of x. But what does this equal? What did they tell us that logarithm base 4x equals? 8. So all we're doing is subbing an 8 into our answer. The answer is negative 8. So if you can remember this identity, questions like this are super easy. Like, oh, that's a reflection in the x-axis. The y-coordinates become negative. That's 8, my answer is negative 8. So if you remember that, you can answer these questions super quickly. But if you forget, we can fall back onto our knowledge of exponents. Okay, part B, they're asking us to solve this exponentially. So we're going to take log base 4, argument x equals 8, and we're going to rewrite that as an exponent. So we have 4 to the power of 8 equals x. We're going to sub that x into the other logarithm. If we do that, we get log base 1/4 of 4 to the power of 8 will be equal to something. Maybe we'll just put it equal to y. We can then put that into exponential form. So we get 1/4 the power of y equals 4 to the power of 8. To solve this, we need a common base. How can I make 1/4 into base 4? Good. 1/4 is equivalent to 4 to the power of -1. So I'm going to change this to 4 to the power of -1, which is now to the power of y as well, equals 4 to the power of 8. Same base. What do I do with the exponents? Set them equal. So now I have negative y equals 8, divide by negative, and y equals 8. Sorry, negative 8. What's another way we could have solved this once we got to this point? You guys remember on your calculator changing the base to 10? You could have gone log 4 to the power of 8 divided by log 1/4. So why don't you guys try that? Just practice. Log 4 to the power of 8 divided by log 1/4 and 0.25. You guys get negative 8? Hopefully. Otherwise you probably put it into your calculator wrong. If you didn't, just let me know. Got it? Good stuff. Alright, so we learned how the base will change by transformation, which is a reflection in the x-axis, if the bases are reciprocals. Okay, 1 over the base. We have transformation looking like a reflection in the x-axis, but now we're going to look at what happens if we don't have reciprocals. We have base 2, we have base 4, we have base 8. We're going to see what happens. So the graph shows us what each of these logarithms look like. So log with base 2 is here, and a logarithm with base 4 here, and a logarithm with base 8 here. So let's just complete the following. We have y equals the log, base 2 argument x, that's going to pass through a certain point. They're basically asking us what is the y coordinate when x is 8. So for 1, we'll have y equals logarithm, base 2, and now x is 8. So 2 to the power of what gives me 8? 3. Good. So we have the point 8, 3. Which is right here. For part 2, they're telling us we're looking at the logarithm with base 4. We have to figure out the y coordinate when x is 8. So for part 2, y is equal to logarithm, base 4, argument 8. We can convert that to exponential form. 4 to the power of y equals 8. Now is there anything that we can put to the power, like 4 to the power of something to get 8? No, so we have to change this to base 2. We get 2 to the power of 2 power of y. That replaced my 4. And 8 is replaced with 2 to the power of 3. Now that we have the same base, we can just multiply these exponents and we get 2y. And if we have the same base, we can set those exponents equal. So we have 2y equals 3. Dividing by 2, we get y equals 3 over 2. logarithm with base 4, when x is 8, we're at 8 and 3 over 2. Emily, where are you at?
I'm just confused. Where'd you get 2y?
How did I get 2y?
Yeah.
So 4 I converted to 2 to the power of 2,
Okay.
but I already had that exponent y out there. So the exponent 2 times y
It's 2.
is 2y.
But what happened to the other 2? You just.
Once the bases are exactly the same, you can set the
Oh.
exponents equal.
Okay, got it.
Sorry, I jumped a step too quick. Alright, let's look at the third one. Okay, this time we have base 8, and they're telling us that x coordinate is 8, we need to figure out y. So y will equal logarithm base 8 argument 8. What do we know when the base and the argument are the same? It equals 1. So we have the point 81. So taking a look at this graph, x is all the same, 8, 8, 8. What's happening to the y's? They're stretching. And the reason why I know they're a stretch and not a translation is because check out this x-intercept. 1, 0. Did that ever move? No. If it was a translation, these graphs would have a different x-intercept. Okay, this point would have moved up or moved down. But it stayed completely the same. So that means I'm going to take a look and compare these points. All the x values are the same, but the y coordinates are different. So that's telling me I have a vertical stretch. Okay, and they're saying that the logarithm base 4 argument x is a vertical stretch of the logarithm with base 2. Okay, how can we figure out that stretch? Well, we can look at the y coordinates. So for base 2, we're at 3. Base 4, we're now at 3 over 2. So how do I go from 3 to 3 over 2? Pardon? No.
Divide by 2.
Divide by 2, perfect. Or we can say it's like multiplying by a half. Okay, dividing by 2 is the same as multiplying by a half. Awesome. Okay, what about going from base 8 to base 2? Base 2 we had y value at 3. Base 8, y value at 1. So how do we go from 3 to 1?
Divide by 3.
Divide by 3. So our stretch factor is 1 over 3. Okay, now they're telling us to figure out d, but I don't think we've quite gotten there yet. I want you to take a look at these bases, and we're going to compare them to the logarithm that we're first starting with. Okay, so the logarithm that we began with was base 2. The next one was base 4, but base 4 can be written as 2 to the power of 2. And similarly, base 8 can be written as 2 to the power of 3. If we compare how these bases can be rewritten, we said that this base can be written as 2 to the power of 2. Do you see any relation between that exponent 2 and maybe what we're dividing by? Or maybe this exponent 3 and what the stretch factor is divided by? Pretty much what it is whatever the exponent is, that's what you're going to divide by in your stretch factor. So if we're starting with logarithm base 2 and we're going to logarithm base 64, let's just convert this to base 2 and we get 2 to the power of what gives me 64? Figure it out. Help me out. No, one more. Good. Okay, so if we're starting with a logarithm of base 2, and we're going to the logarithm of base 64, what do I have to multiply this by to get that? Stretch factor of what? Look at the pattern, what have we been doing?
1/6.
Good, it's 1/6. And to make this a little bit more obvious, I could rewrite this as base 2 to the power of 6. So whatever the exponent is on the common base, that's going to be the reciprocal stretch factor. Which is stated below. So the transformation which maps y equals the logarithm with base b to y equals the logarithm with base b to the power of n is considered a vertical stretch about the x-axis, and it will be by a factor of 1/n. 1 over your exponent on the base. Okay, so see how we had b to the power of n? The stretch factor will be 1/n. So given that we've gone through a few examples, let's try a few more to see how you guys do. We're starting with logarithm base 3. We're going to a logarithm base 81. What should I convert first? 81 to base what? 3. So if we're comparing it to base 3, we want to put this in base 3. So if we rewrite this, we get logarithm base 3 to the power of what? 4. Good. So if we were to compare the two, we would just take whatever the exponent is. The stretch factor will be 1 over that exponent. So we can say that logarithm base 81 is equal to 1/4 of logarithm base 3. Okay, how could I rewrite 16? 2 to the power of 4, or if we have base 4 already, 4 to the power of 2. Okay, now just keep in mind, we talked about the reciprocal. If I wrote it using the reciprocal, I would say it's 1/2 of the original logarithm is equal to my new logarithm. But if I move this half to the other side, I would have to multiply by what? 2. So this is actually equivalent to log base 4 is equal to 2 times the logarithm base 16. And it's always the stretch factor multiplied by the smaller base is equal to the logarithm with the bigger base. So if we were switching that order, we can take the stretch factor and just multiply it up. Similarly, how could I rewrite this so that I had a stretch factor times the logarithm base 81 of x equals log base 3 of x? What would I do with that 1/4? I'd multiply by 4, right? So the stretch factor would be 4. So given those rules, we should be able to solve this question in about 3 seconds. That fast. Don't worry, there is a backup way if you forget. Okay, we have logarithm base 5 equals 6, and we have to state the value of logarithm base 125 argument x. So sure, we can solve that using the exponential form, but we're going to use the little trick that we learned, and I'll just rewrite it. So logarithm of our base is equal to 1/n times that. So we have a stretch factor of 1/n of our original logarithm is equal to logarithm of our base to the power of n. Yeah.
I'm just confused on like the bottom of the last page.
Yeah.
When you have like log of 4 of x is equal to 2 log 16 x,
Yeah.
because isn't log of 16 bigger than log of 4?
It is.
So then why do you have to multiply the 16 by 2?
Let's just take a look back at the graph here. What do you notice about the bases and where they're located? The smaller the base, the higher the number. The greater the base, the lower the y value.
Why though? Because like when you calculate them, they're bigger.
I guess it's because it's the inverse of the exponential function. Like if this was an exponential, as x grows, y grows too. But because it's working as an inverse, it's growing kind of exponentially in an opposite direction. So because of that, how do I word this? I guess just by looking at the pattern, do you remember we had 8-3, 8-3 over 2, and 8-1. Okay, do you see how the y coordinates are getting lower as the x or as the bases are getting higher? Okay, they're getting lower as the base numbers are getting higher. So that's just the trend of it. So if we had log 16 of x, that'd be even lower. If we had log 32 of x, it'd be even closer to that x-axis.
Like, because I put in log of 16, and it's a bigger number than log of 3. So how do they graph like that?
Just keep in mind that log 16, if you put that in your calculator, that's assuming the base is 10. Whereas here, we're actually changing the base number, not the argument number.
Okay, that makes more sense.
Okay, so that's probably why it's not making sense on what you're seeing on your calculator.
Okay, that makes more sense. Thank you.
If you did want to graph this, it would look like log x over, say, log 8, or log x over log 4.
Okay.
Which we're going to get into a bit of graphing at the end of the lesson.
Okay, that makes more sense.
So sorry, the 3-second question. So we have to figure out the value of logarithm base 125 of x if we're given logarithm base 5, argument x equals 6. And we're going to use this identity to figure it out. Imagine that this 6 wasn't given here, and we just had log base 5x and log base 125x. Would we say that these are vertical stretches of each other? Yep. So we're going to convert this to 5 to the power of 3. And we're going to take that exponent. I'm just going to replace it on the side here. So if we have log 5 of x equals log 125x, what's the stretch factor on this if the exponent's 3? 1/3. Good. Okay, but what was log base 5x equal to? 6. So we have 1/3 times 6. That's going to be the value of log base 125 argument x. 6 divided by 3 is 2.
Where's the 1/3 come from?
So based on what we looked at in the last example, this identity here, we figured out that if they have the same base and it's raised to an exponent on the other, then there's a stretch factor of 1 over n. And so if we look at 125, we can convert that to base 5 to match the other, but it has an exponent 3.
Should the base be 5 on the instead of 125, or do you keep it?
You can keep it as this. This is equal to 1/3 of the original base 5. And then they told us the value of log base 5 was 6, so I've just subbed that in. And I've multiplied by the stretch factor 1/3. 6 times 1/3 gives me 2. So I know we just learned this, but if you can remember it, it will make this question so much easier to solve. If you can't though, there is a backup. We can use exponential form to figure it out. So first we're going to take the fact that log base 5 of x equals 6. We're going to convert that into exponential form. So we get 5 to the power of 6 equals x. We're going to sub the x back into the second statement they tell us, logarithm 125 x. So if we can replace x with that, we'll be able to solve. So log base 125, and now x is 5 to the power of 6. We should be able to solve this. And there's two ways. We can just plug it in our calculator and go log 5 to the power of 6 divided by log 125. Okay, so option 1, log 5 to the power of 6 divided by log 125. And what do you get? 2. Good. Okay, or we can keep going with the exponential form. Set this equal to y. And then we have our base 125 to the power of y equals 5 to the power of 6. Then I convert 125 to base 5. 5 to the power of 3 gives me 125. If I have the same base, what can I do, Emily, with those exponents? So if I have the same base, what can I do with the exponents?
Set them equal to each other.
Good job, Jose. What is this actually?
3y.
So I have 3y equals 6. I'm going to divide both sides by 3, and I get y equals 2. Okay, sorry it's so all crammed in there. So there's actually 3 ways we could have solved this question. You get to pick how you like to solve it. But someone in the other class asked, well, do I have to solve it this way? Can I not just go about it these ways? Sure, there's 3 ways you can solve it. You can figure out which way you like best. But what if this was a conceptual question where they're testing you on your knowledge about this? Knowing that this logarithm is basically the base logarithm with the stretch factor. So you kind of have to memorize this identity, because there will be conceptual questions about that as well. This next question, you just can't get away from transformations. Okay, so unit 2 is going to be coming back over and over and over throughout the year. We're now going to look at logarithms and figure out how they look as we apply different transformations. So just as a review, take a look. We have y is equal to a times the logarithm base c times b of x minus h plus k. So reviewing, who can tell me what the a stands for? Say it with some confidence. Vertical stretch. B.
Horizontal stretch.
Good. H.
Horizontal transition.
Good. And K?
Vertical transition.
You guys got it. All right. Now that we reviewed that, we did okay. We can just look at the base graph here, which is logarithm base 3 argument x, and we are going to apply a few transformations to that graph. So what is this 2 telling us?
Vertical stretch.
By what?
Factor of 2.
About what?
About the x.
Very good. So just reviewing our point mapping, because that's really important. X, y will be mapped to
2x. No, 2. Oh my gosh.
what's stretching? Vertical.
2y.
Okay, good. So x will stay the same. Y is going to be stretched by a factor of 2. Everyone's just relying on you, Hannah. It's not very fair, is it? Okay, Xander, you're gonna help me on the next one. We started with logarithm base 3 of x. Okay, now we have logarithm, same base 3, but instead of x, we have x minus 2. Awesome. Okay, so we have a horizontal translation, 2 units right. So Jane, if we're moving 2 units right, what will your point mapping look like?
The x-axis? 2x?
We're moving 2 units right, so is that going to affect the x value or the y?
Yes.
Good. So
X plus 2.
x will be x plus 2. Will y change? No. Good job. Okay, and the last one here.
Zach Manuel to the front office, please.
We have our original function, and then we're subtracting 2. Joseph? What's happening in this one?
It's going down.
Good, so it's a vertical translation down 2 units. So Jared, what's your point mapping going to look like?
The x is going to stay the same, and drama minus 2 is going to go up.
Awesome. Okay, so now that we've talked about all the transformations, let's actually move this graph with the transformations. So, going back to the first one. We have a vertical stretch by a factor of 2. All the y coordinates will be multiplied by 2. So let's just take a look at a few points. We have an x-intercept at 1, 0. We have another obvious point at 3, 1. And then another obvious point at 9, 2. Okay, so those are all points on our original graph. Let's use our point mapping to move the graph by a vertical stretch of 2. So if we're multiplying by all our y values by 2, will this x-intercept change? No, that one's going to stay. Okay, what about here? 3, 1 will move to?
6, 1.
We're multiplying
Sorry.
the y coordinates.
3, 2.
3, 2, good. Okay, and then 9, 2 will go to? 9, 4. Awesome. So we're going to approach the y-axis, which is our vertical asymptote. We're going to go through the x-intercept and through our 2 new points. Why not label it? Y equals 2 times logarithm base 3 argument x. Okay, can we all agree that this is our vertical asymptote?
Yeah.
What's the equation of that vertical asymptote along the y-axis? Good. X equals 0 is our vertical asymptote. So let's just see what happens when we move the graph 2 units right. Okay, all the x coordinates will be adding 2. So if we started at 1, 0, we have to add 2 to all the x coordinates. Now we're at 3, 0. Okay, this point here, 3, 1, will now be at 5, 1. And this one will be at 11, 2. What's going to happen to the vertical asymptote? It's going to move. Okay, if the graph is shifted 2 units right, then that means your asymptote is already also switched. Okay, so let's just draw through. We're going to approach our vertical asymptote, which is now at x equals 2, and go through the points that we just mapped. And then we'll label it. Y is equal to log base 3, x minus 2. Now we've got 3 graphs on there, but we're going to try and fit one more. We're now taking the original graph and we're moving all the y coordinates down 2 spaces. So looking at our original points, make sure you're careful with what are your original points. We started at 1, 0. If we move down 2 spaces, we're at 1, -2. Okay, 3, 1. If we move down 2 spaces, we'll be at 3, -1. And 9, 2 on our original graph. If we move down 2 spaces, we'll be at 9, 9, 0. Will the vertical asymptote change? No. So we're going to approach the y-axis and go through the 3 points that we've just moved. And then label it. Y equals our original logarithm minus 2. Joes, did I make a mistake? Okay, any questions? Which one are you?
No, it's not.
You're good? Okay. If you have a question, let me know.
Yeah. Shouldn't it be 5, 2, though? So
Where-
5, 1?
Which one? This one? So we're at 3, 1 on our original graph.
Yeah, and so then it should be 3, 2, right?
Are you talking about this one?
No, because that's the one that's
Okay, I think you did it differently. It's never mind.
Did you get the same points though?
I just did a different process of this, but no, I get it. It's okay.
Well, you should have the same points.
Yeah.
What's your
I think
process?
No, I get it. Don't worry. It's good.
Okay, I might come see you after just to make sure you're doing it right. Okay, taking a look at all these transformations, we need to figure out, did any of these transformations change the domain or range? Let's just start with range. Are all the graphs going to infinity and down to negative infinity? So the range, no change on any of the transformations. Was there an example where the domain changed? Which one? Okay, so the domain changed on example 2 when we moved right 2. The domain changed from x is greater than 0 to x is greater than 2. So there was only a domain change when we moved the graph horizontally left or right. We've talked about this throughout the lesson, but just to summarize, for the first transformation when we had a vertical stretch by 2, what was the equation of the vertical asymptote? Yeah, x equals 0. It's your y-axis. All of that graph was doing was approaching the y-axis. It's not going to touch the y-axis. It's not going to cross it. That's why it's a vertical asymptote. I'll get into a little bit later why we have that. Okay, we moved 2 spaces right. We already talked about it, how if we move 2 spaces right, then the vertical asymptote also changes 2 spaces right. So we're now at x equals 2. And the third transformation, we were moving down. Okay, that's not going to change where the graph's approaching. It's still going to go vertical asymptote, which is x equals 0. So Joe, is you sure there's no questions?
Yeah, don't worry. I'm good.
Last question, don't worry.
Do you want me to pick that up?
That'd be awesome. Thank you.
Yes, it's